Okay, thank you very much for inviting me to make contribution to this webinar. My name is Dr. Wang. I'm at University of Salford in Manchester, UK. Today, I would like to brief one of my main theoretical work in the hydrological characterization of porous materials. So I give it called the technical note. It's some of recent concept I formed regarding my previous work. It's a technical note on the water vapor adsorption and water retention characteristics of unsaturated porous materials. Okay. Water state in unsaturated porous media or materials is a fundamental issue of wide interest. For example, for environmental hydrology, water management, and slope soil erosion and soil contamination of soils of field and infrastructure durability and the geothermal use, the green energy. So, and more. Actually, the vapor adsorption and water condensation in pores are the two fundamental mechanisms which underlines the hydraulic state of unsaturated porous materials. And the water state in the porous materials under unsaturated state include the three phases. One is a vapor, and one is a condensed bulk water, and the water film on the empty pore surfaces. So there are two constitutive characterizations for the two mechanisms. The first one, which is a vapor adsorption isosen, which is also called the T-curve, which reflected or defined the water volume on unit surface area or water film thickness on the substrate surface or pore surfaces versus against the vapor relative humidity. The second one is about the water retention characteristic, which quantify the water content, the bulk water content under the unsaturated state, with the suction of the porous materials. There are quite a lot of research has been done in this area, and this is since early of last century. So conventionally, there are three. Here there are more than three, but here I list three, which is has some representative of the previous research. The Harkins jury and Finkel, Horsey Hill models, and these two are can be classified as empirical models, and another one is a popular one, which is called the BET model. So which quantify, these are used to quantify the film thickness on non-porous substrate against the vapor relative humidity. Also, there has also quite a lot of research on the water retention characteristic of porous materials. And also there are many research work and proposed quite a lot of models. For example, the most popular one, which is a Wang formula, so which is based on an empirical concept. And on that, because there is no solid foundation for that, so people also considered another one, which is related to the water retention characteristic with the pore size distribution, such as the Friedland-Shim model. And for these previous two models, they didn't think about the water film effect independently, it's an independent effect. So there are some of improvement on that. So for example, some model consult of the water film effect on the total water condensation and the water retention characteristic effect. The water retention characteristic or water retention curve plays a very important role, which can be used to represent or analyze the pore network property of porous materials, such as pore site distribution, and also has been employed to predict the hydraulic conductivity, the hydraulic property of porous materials. However, the conventional approaches are still open for improvement. For example, there are two key issues hasn't been fully addressed yet. First one, which is how to quantify the water film effect on the water retention curve, which is still a challenge. And the second one, I noticed that there hasn't had a uniformed model to describe the consistency between the water vapor adsorption and the bulk water retention in pores, even though both of these are undefined by the same interfacial mechanism. So actually we say the water state in unsaturated porous materials, which has a lower potential than the water in the open free space. So the water retained in the pore spaces has a matrix potential, which consists of two components. One is a bulk water component potential, and another one is a water film component. Both of them form the total water matrix potential inside the pore spaces. So actually the matrix potential of the pore water can be determined in terms of the pressure of the three phases inside the pore. So in terms of the mathematical expression, so the matrix potential of the pore water inside the pores consists of the bulk water pressure, or bulk water potential, and the film water potential, and which can be quantified as a water pressure, bulk water pressure, plus the film water pressure, and minus the bulk vapor pressure. And the difference of this pressure, which is actually balanced by the meniscus or the interfacial or the surface tension on the interfacial of the vapor and the water phase Now, this is a kind of concept we understand the pore water state in terms of interfacial physics. So we have said compared to an open free state, water on pore surfaces or water in pore structures has a chemical potential change. And this chemical potential change actually can be evaluated using the Kelvin equation, as we illustrated here. So this is a solid substrate, so we can think it as the solid phase of the pore materials. And this is a water phase, in standard bulk water and the water film inside the pore. And this is a vapor phase inside the pore spaces, empty pore spaces. And the three phases has a relationship which can be evaluated in terms of the Kelvin equation. So that means the chemical potential change of the adsorbed water film or bulk water on the substrate pore solid phase can be evaluated using the using the exponential function in terms of the relative humidity of the vapor coexisting inside the pore. So that means we can use the previous vapor or previous Kelvin equation to describe the vapor adsorption or the T curve. So actually we say in terms of the mean field model for adsorption, the gas here the gas stands for the vapor, water vapor. The gas adsorption of a substrate surface is driven by ground potential. The ground potential is equivalent to the potential change we mentioned before, and the equilibrium thickness of the water film or the wetting film on the substrate adsorbed surface can be estimated using the following equation. And if we rearrange of this equation and we take in the parameters, this is interfacial physical parameters, the ASVL, and also the vapor density or the water density and the vapor density, and we take them as a constant. So we can rearrange of this equation. So that means the water potential change or the ground potential of the water film inside the pore spaces or on the pore substrate, solid substrate, can be quantified using this power function, And we substitute the power function back to the Kelvin equation. So that means we can get the expression of the thickness in terms of the vapor relative humidity, the exponential function, And however, the previous function, this one, the equation one, hasn't considered of or could be neglected the other effects such as electrostatic and surface structure, and also the range of the disjoining force. The disjoining force means the molecule interaction or van der Waals forces. And so if we incorporate all of these concepts or effects into the first equation, then we can get the more general formula, the equation 3 for the relationship of the vapor phase, relative humidity, and the coexisting water film on the substrate. So actually we say the equation 3 stands for characterization represent the water adsorption isosen, or it can be used to quantify or characterize the T curve. Now, for example, we're using the equation 3 to fit some of the experiment of the water absorption of solid substrates, and compared with other 3 models we mentioned before, the HJ model, FHH model, and the BET model. And so the vertical axis represents the thickness, the statistic thickness of the water film on the substrate, and according to the water vapor relative humidity. And from here we can say the equation 3 present quite good, can say the one of the best among the compared with the 3 previous proposed model. And we also zoom into the early part, under the very high or very low relative humidity, and compared with the DET and the equation 3. So we can say at the very low relative humidity, and the equation 3 presents much better representing of the T curve compared to BET. So that means here we can get a conclusion: the equation 3 demonstrates the best in the whole range of T curve compared to previous models. Now we talk about the water retention characterization. So conventionally, water reside in pore structures. So we relate them in terms of the pore size distribution. However, to understand or quantify the pore size distribution, we should simplify or represent the pore size, pore structure as well. So there are 2 typical pore size representation. The one is a bundle cylindrical capillary model, so which use a straight capillary tube to represent the individual pores. And another one is called the pore network model. And also there's another one which is could be say among the compared to other 2, which is much simple, but however, which is a standard the fundamental interfacial physics. So that means for this modeless model, so we just represent the pore spaces using a single capillary, and the capillary radius defined by the ratio of the total pore volume and the total surface area inside the pore structures. And with this kind of modeless model, so the pore size variation can be understood as quantified or evaluated in terms of the length, the change of the length of the specific water content variation. So now, because if we're using a modeless model, so that means we can represent the pore size or the pore structures inside the pore or inside the porous media with a certain radius. So with the concept of a certain radius, so that means we can directly take in the T curve model before, the Kelvin equation, So the delta UWB, which stands the bulk water state, the chemical potential change or grand potential inside the pores, and which relate to the certain radius of the representative modeless model. And also the water film, so which is still standards for the chemical potential change in terms of the thickness of the water film on the empty pores. And we also can apply the Kelvin equation in terms of the certain radius of the modeless representative capillary and the chemical potential change and the Kelvin equation. Okay, so now in terms of that, so that means we say the water potential or metric water chemical potential inside the pore spaces can be quantified in terms of the three phases, the pressure of the three phases, the water phase, the water film phase, and the vapor phase, and the water and the vapor phase based on the moldness capillary of the certain radius, so which can be quantified in terms of the Kelvin equation and the chemical potential change or the ground potential of the water phase and the vapor phase respectively. And so far we haven't had, and also we say the vapor phase or the water film phase, we can still using the T curve to represent it, With this kind of understanding, so we say the state of the water phase can be evaluated in terms of the integration over the pore surfaces area, in pore surface area. So if we taking a representative elementary of the porous material. Okay, so in terms of this kind of understanding and the treatment, so that means we can quantify of the ground potential of the water phase in terms of the pore side, or in terms of the water saturation, Yeah, and we substitute that into the Kelvin equation. So that means we can specifically or we can explicitly describe the water phase pressure inside the pore spaces in terms of the water saturation degree, Yeah, and the delta UW here, which is a molar commercial change, which depends on the representative or hydraulic radius of the moldness model, and the delta U0, which stands for the initial water film, which covers all surface areas before the condensation of the pore water. And as we have mentioned about, because we say we're using a single certain radius capillary to represent the real complicated pore structure. So that means this equation also can be applied for the pore phase or vapor phase as well. So that means at last we can obtain the vapor phase in terms of the water saturation. We say the SW is a space occupied by water, and 1 minus SW, which is a space water occupied by vapor. So actually, so far, all the description and all the quantified the mathematical formula, which is defined under the pore scale. So for the bulk materials matrix potential, we need to upscale the pore scale quantify formula up to the bulk material scale. So here we follow the volume average theorem. So we integrate of the pore scale matrix potential over the all pore spaces, and divide the volume of the representative of the materials. Now we get to the average. We can get the pore the bulk material scale matrix potential of water. Okay, and then we can substitute all the previous pore scale definition for the pressure of bulk water, pressure of bulk vapor, and the water film, and we integrate all of this formula, and then we can get this expression. So this is a which is standards for the water retention characteristic of the porous materials, and in terms of the water saturation. There is still challenges how can we quantify the vapor pressure? Oh, not the water film pressure. Because we say the water film pressure is in terms of the thickness, but the thickness, which is very hard to quantify in terms of the vapor pressure, and how to quantify it in terms of the water saturation. So we suggested using this simplified power function. So that means we represent of this average volume integration for the water film using this power function, and then quantify the water film factor in terms of water saturation, the bulk water saturation. So in terms of that, so finally we can obtain expression of the matrix potential in terms of the constant parameters, which determined by the nature of the porous material and the water itself, in terms of the interfacial interaction, the alpha, beta, and the lambda, which stands for these parameters, and the water film effect, the last term. Okay, so this is a test of this model. So compared to with the previous work, I didn't consider of the water or the film effect specifically. So I ever proposed the model just consider of the vapor phase and the water phase. And for this three-phase model, so we revise of the previous work using a power function to reflect the water film effect. So compared with the previous work, so we're using the two models to fit the water retention curve of unsaturated soils. So we can say the three-phase model presents a quite good representation for the water retention in the whole range, from the very low or very dry situation to the high water content, So there's a conclusion. So a brief conclusion, we say the vapor adsorption, isosen, and water retention characteristic of porous material can be unified on interfacial physics and the Kelvin equation. And the proposed T-curve model presents a better representation than BET models in the whole range of relative humidity of the vapor, and the water retention characteristic of the unsaturated materials, which is determined by three phases of the water coexist in the pore spaces and the pore surfaces. And the developed three-phase model present a good representation of the unsaturated water retention characteristic and the water retention curve. However, further research is still needed. So about how we interpret or how we understand of the parameter data we obtained from using the fitting approach, using the data or using the formula to fit the experimental measurement. That's all. Thank you very much.